I think you can go ahead.
Is it timer automatic?
The 15 minutes.
How to kick off the timer?
Because it's a good feature.
Let's see.
You can start right now.
Yeah, let me just.
Okay, you can just put the time. You see, it says 15 minutes. You see.
All right.
Okay. Good morning, everyone. Thank you all for being here. This is a ICTP-SAIFR South America site of ICTP, and this is a joint session with Brazil from São Paulo, streaming from São Paulo. And the topic is quantum technologies. So we're going to hear all the way from quantum error correction to qubits and code atoms. There will be 3 speakers speaking from the Anaheim site and 3 speakers from Brazil. It will be broadcast to us through the screen. And the first speaker is Fernando Brandão from Caltech and AWS Quantum. Fernando, the floor is yours.
Thank you. Oh, sorry. Okay, hi everyone. So I'm going to talk about an experiment that we did at AWS, and we posted a paper end of last year. And to motivate, eventually we want to build a quantum computer, right, that can run interesting applications. And for doing that, we need error correction for the error rates to be low enough. And there is one traditional approach to error correction, which is to encode qubits, right? Use redundancy in the number of qubits that you have. For example, using what we call the surface code. There is a picture of the surface code there. And the idea is that there is 2 types of errors that we have to correct in the quantum regime. There is Z errors, phase flip errors, and X error, bit flip errors. And then we can, measure some qubits, try to detect errors and correct for them. And there is a price to pay. There is an overhead, right? So for one logical qubit that we have the computation, we need many physical qubits. So it's nice that this can work, but this overhead can be quite steep, right? Which means that maybe to build a useful quantum computer, we might need millions of qubits. So is there a way around this, right? This big overhead. And one idea that has been explored in the last decades is to try to devise some architecture which has bias noise. So we have these 2 types of errors that I mentioned, Z errors and X errors. And now we can try to find an architecture which has some large bias in the noise. So in the sense that Z errors, they are much higher than X and Y errors. And why that would be interesting if you can find this kind of architecture, because as I mentioned, right, so kind of one dimension of the surface code is for correct Z errors, the other one is to correct X errors. So now if you have some bias, suddenly, right, in the direction of the error that is more rare, like the X error, you need like a thinner, right, number of qubits. So this is like rectangular surface code. And in the regime of infinite bias, you don't have to correct one type of error. And now you can just use a classical code, for example, a repetition code. So you go from a 2-dimensional, right, array of qubits to just a line of qubits. And this can lead to, like order of magnitude improvement in the overhead. But then the whole question is, okay, can you get systems that have this bias noise, right? How you do it, and how you do error correction with bias noise. And there is one idea which started being developed, actually even before that, already in '94, there were some papers about this, but that paper from Miharim and collaborators from 2014 fleshed out the idea in more detail, is to use cat qubits. So now instead of qubits, you use a state of harmonic oscillator, and you use as your computational basis coherent states of mean photon number alpha square, but with different phases. So 0 is plus alpha, 1 is minus alpha. It's not exactly that, right? Because they are not really orthogonal, but they're very close to orthogonal. So the way you actually define is plus and minus as the plus and minus combination of them. And then suppose that physically you can engineer what we call a 2-photon dissipation. So you have a dissipative process there where you lose photons in pairs. Okay, so instead of using just 1 photon each time as you do, right, like typically that nature does, you engineer that you lose photons in pairs. And you also put some kind of 2-photon drive. Then there is 2 dark states. There is 2 steady states of this dissipative dynamics, and they're exactly alpha and minus alpha. So now you have this manifold, right, of states which are dark, This is the complementary basis that I mentioned before. And what you see is that when this dissipation is on, bit flip errors, which is the probability they go from alpha to minus alpha, it becomes exponentially suppressed in the size of the cat in alpha square. So kind of at the hardware level, you're correcting one type of error, right? Bit flip, X errors. And you still, if you have a photon loss, plus becomes minus, so you still have dephasing, right? You still have Z errors. But it might be an easier job for you. And what happens, what you can see is that you increase alpha square, the size of the cat, bit flip errors are exponentially suppressed. Phase flip errors, they actually increase, but they only increase linearly in alpha square. And then you have a gain, right? So you are exponentially biased the noise once you do this. And you can try to use this for error correction. So this is what I mentioned, right? So you have the probability of X errors. There it's exponentially small in alpha square. Of course, goes as kappa 1, which is the loss rate of your cavity. Z errors increase linearly in alpha square. So your bias is exponential alpha square. So just some history, right before we go to our work at AWS. There was this theoretical proposal in 2014. There was beautiful experiments, first experiments from people at Yale in the following years. But then the first time that we saw this exponential suppression of bit flips was this experiment from Paris, where you saw bit flip rates going from 2 microseconds up to 1 millisecond by increasing alpha square. Then there was an interesting theory paper proposing an error correction scheme using these dissipative caps that we follow. I'll tell you more about it. And then there was more recent experiments where you even see like 100 seconds bit flip time, but you need some fairly large mean photon number. And also like 10-second bit flip times with more manageable mean photon number of like 10. Where you go from 70 microseconds initial bit flip times to 10 seconds. So this kind of exponential stabilization of bit flip errors, people have seen that in the lab a lot by now. So let me just jump this. All right. So we trying to do some error correction, right? We correct bit flip errors using these passive caps, but we have to correct phase flip errors as well. So the idea that we want to implement is that we want to build a chip where you use resonators, right? Use resonators as data qubits. This is where we put the cat and we try to correct for bit flip errors there. But now we have to correct phase flip errors actively using like measuring stabilizers, doing error correction. And for that, we need ancillas. And in our case, we decided to do ancillas, a transmut as ancilla, like pure qubits as ancillas. Because then the interactions that we need, they are easier in this case. And to measure then errors, phase errors or Z errors in the cats, we use just the dispersive interaction of the transmut with the cavity mode. You say, well, but you have to be careful now, because if there is a decay from E to G, right, in the transmut, you will dephase your cavity mode, and then this will lead to a Z error. That's not what you want. So you have to use the transmut in a more clever way, which is you use 3 levels of the transmut, and you basically do what we call a chi matching here between F and E level, such that the E and F level they interact in the same way with the cavity mode, the same dispersive interaction chi. So if there is a decay from F to E, it doesn't dephase the cavity anymore, right? Because the cavity keeps rotating. So that's a way where you can kind of detect the errors without spoiling the cavity using the transmut. And that's what we try to build. So we'll be working at AWS for a few years, trying to build an experiment that implements this idea. And I want to tell you a little bit about it. So this is the schematic of the device that we built. We have we call data qubits, are these resonators that have these cat qubits. There's 5 of them. We have this what we call buffer mode. This engineer this 2 photon dissipation between the cat qubits, right? So it makes cat qubits lose photons in pairs. And we have this transmut qubits that is used as ancillas with this dispersive interaction that I mentioned before, right? That basically measures the parity of 2 resonators and see if there were Z errors. So again, right, phase flip errors will be detected by this repetition code. and bit flip errors are suppressed by the cat qubits. So this is kind of a picture of the quantum device that was built. So our device has, we could go up to distance 7, but then, we found a patch of distance 5 that actually worked better, so we focused on that. So that's actually a picture of the chip. So it's like a flip chip architecture. So we have a top aluminum chip where we have like the nonlinear stuff, right? So we have the transmons, the buffers, the couplers, and we have a bottom tantalum chip, which has these coherent resonators, and tantalum because we want a high Q, right, for the resonators as high as we could get. This is what we could get. So for the storage, which means the resonator, they are these blue shapes, right? They're these kind of big strip line resonators that we built. We can get like 70 microseconds coherence time. For our transmons, which are the oscillators, we got 30 microseconds. And something very important was we need some very delicate frequency targeting here to get this Chi matching to work that I mentioned before. So we got some frequency targeting within like 50 megahertz for the frequencies of the resonator and transmons. So let me go a little bit quicker. So this is just a picture, another picture, right, of the unit cell. So we have the resonator, it's very large. We have the buffer here. This is a filter that we have to build such that the buffer has to be very lossy, right, because it leads to the two-photon dissipation. But we don't want that this becomes a decay channel for the storage resonator. So this filter does the job. And here, I'll zoom in, but there is like transmons and couplers for the oscillator. So they are much smaller. Okay, so just before that, actually, this is what we got, the single cat performance. We see this exponential improvement in the bit flip time of each one of the resonators, right? It goes from this kind of 70 microseconds that I mentioned up to the way, like like a second in the experiment. And here you have this 1 over alpha square, right, behavior with mean photon number for the phase flip error that we also expect from theory. So this, like zooming in again, right? This is the chip kind of with this is the transmon oscillator. We use couplers to switch on and off the dispersive interaction. They are also transmons. And of course, we have a readout resonator as well. So let me just go, okay, so let me just show you a plot of the actual result. Time is up. Then go to the last slide. Okay, so putting everything together, we saw this kind of plots. So here we have the bit, sorry, no, actually, let me show you the next one. This one. So we have the logical probabilities of error now of running our repetition cat code experiments, and we can vary, of course, the mean photon number, alpha square, and then we compare the results for distance 5 code, right, using 5 resonators versus distance 3 patches that we also had there. So red and blue are for the distance 3 patches, right, and purple is for the distance 5. And then, of course, for each alpha square, we have a logical probability of error, which is the total X and Z logical probabilities of error. And then we can optimize each one of them for alpha square, right? So basically, alpha square is a free parameter, the mean photon number. We should choose the one that minimizes the logical probabilities of error. And then we found that, they are kind of roughly the same. With distance 5 is a little bit better, but only marginally better, right? This should have been something else. There's a typo here. This should be like 1.6. Well, 1.71 if I remember correctly. So there was like, a tiny improvement, which is what we expect from error correction, right? But of course, we like to see a big improvement, and for that we have to work harder, and it's what we want to do next. But we could, we were happy we could demonstrate for the first time this kind of concatenated bosonic error correction, right? And it's kind of in the regime where error correction starts to give a gain. So the next step is to really drive this more, right? Improve the performance of the components, and and see this logical probability of error going down and down. So this is our error budget. I won't go through it, but there's several core components that, right, we think we can decrease a lot in future experiments. We think like the red, for example, should be completely, we can mostly get away with it. Blue, should be able to reduce by a factor of 5 at least. So we expect that we are in a good position to make further improvements. And with that, I thank you. This is where this work was done in the AWS Center for Quantum Computing. And thank you very much.
So we can take a couple quick questions. We'll try to do one here, one on the Brazilian side. Let's see how that works. Yiwen, please.
Thanks, really nice talk. Gustavo?
Oh, Dario, wait a minute.
Yeah, do we have chance to ask questions or we go first? How?
We have one person here asking one question, and you get the next one, okay? We got one question here, and you get the next one, Dario.
Okay.
Okay, I'll try to be fast. I was just curious. So you showed, I guess, for a single qubit, you went up to alpha squared about 5, and then for the multiple qubits, about 3.5. Can you just say quickly in those two cases what limits you from going to larger photon?
Yeah, we can always go to larger photon numbers, but there's two things that happen, right? So first, bit flip errors, they're exponentially suppressed, but then they actually plateau at some points because there is some source of error that we actually don't completely understand yet, but they plateau around 1 second right now. So it doesn't pay off to go to alpha square more than 6, for example, because then it just plateaus. But then when you increase alpha square further, then the errors, they increase linearly, right? And then the repetition code has to correct for them. So there's kind of a trade-off they have to do, right? Like, you want to have alpha square small because that makes it easier for the repetition code, but you also want to have it big because then bit flip errors are corrected, right? And then you have to optimize over this. But
Your turn, Dario.
Okay, do we have questions here? Okay, apparently no, so you have again the ball.
Okay, thanks, Fernando, for
Thank you.
talk. Let's thank the speaker again. Next speaker in the queue is Simon Groeblacher from Delft University.
Where is my talk?
I forgot the bottom here.
Here. This one. How do I make this full screen?
On the right, yeah.
This one? Tamanho real. Essa aqui?
Yeah.
Vale. Okay, muito bom. Microphone here? Yes. And this mouse works as well? You're taking away my time. I have so little. Okay, great. Okay, thanks, Gustavo. Thanks for the invitation. Super happy to be here. I unfortunately have to stay here because I have a lot of transitions and I made a PDF. Let me dive right into this. Essentially, this is a collaborative effort between multiple companies, but also between my group and a company in Delft, QFox. Essentially, it's about controlling and reading out the states of superconducting qubits with light. Let's see here. So this is not quite a fair representation of the challenges that quantum computers face, superconducting quantum computers. This is the fridge, the computer from Google in 2021. You see a lot of cables, really hard to scale this to bigger systems, right? This was, I think, for 50 or 60 qubits. So it's going to be really hard to get this to thousands or hundreds of thousands of qubits, of course. So that there is kind of two approaches on how to make this bigger. Of course, you can think of how can we do this with an individual system? How can we replace some of these fibers, these amplifiers? This is more what I'm going to talk about today. But then as a long-term vision, can we connect multiple of these small-scale fridges together and then kind of build parallel processing units out of these quantum computers? And this is kind of the longer-term vision that we have at QFox. Through quantum transduction, we envision creating entanglement links between multiple of these computers through room temperature optical connections, eventually going, of course, from not just computers, also to real quantum networks where you can connect heterogeneously multiple different technologies together, find new applications, computers, for example, with memories, with many different techs essentially together. This is here kind of the vision that IBM laid out a few years ago, kind of have clusters of individual computers connected together with optical links between them so you can really build eventually a universal quantum computer. The key that I think here is really critical is modularity. So think about building small scale systems that you can modularly connect together and build the system size that you will actually need, right? Now, but let's look a little bit at what is actually one of the main challenges of building these bigger systems inside an individual cryostat. So if we just look back if we peel back some of these layers, we can see the main things going in, sorry, everything is a little bit small. The main things going in are essentially cables, coax lines for readout, for control, and for flux biasing of these superconducting qubits, right? There was recently a paper on the archive kind of breaking this down. How many of these lines do you need to control qubits? So for example, for 144 qubits, you need more than 600 coax lines going into these cryostats. So this is again for the readout, for the control, and for the flux biasing. So qubits and tunable couplers as well. So this is quite challenging, not just from the number, but also from the heat load that these introduce. And this is the plot that they had here. So read at each and individual stage, you can see different contributions of these coax lines going in. You see essentially the static heat load. So this is the passive heat load just from the metal wires going into the fridge, right? So this is already a huge thermal budget on the cryostat. And then in addition, you have other contributions, of course, and I want to highlight another one, which is here the low noise amplifiers at the 4K stage. This is really killing the size of the fridge, right? You can't go any bigger depending on the cryostat, of course. This is, I think, from an XLD1000, the Blue Force system. Even if you make the system bigger, you run into similar issues just with a few more qubits. So replacing or supplementing some of these coax lines would be really beneficial. And one idea that the field has been recently pitching quite a bit is using optical fibers for this, right? You can kind of reduce the passive heat load by orders of magnitude by using, instead of metal wires, essentially glass that has no thermal link to the cryogenic environment. Then you can also multiplex these systems, so you don't have to use a single fiber for each qubit or for each line. You can run multiple channels per fiber. So this is really promising to scale. However, of course, then you run into another challenge, and this is, of course, converting RF signals into an optical signal and then back into an RF signal. And while doing all of this inside a cryostat without heating up the cryostat, you're putting in light now, right? So this can be challenging. There's been some interesting proposals and first demonstrations, in particular around optical control of superconducting qubits. This is from John Teufels's group at NIST, essentially showing that you can, if you use a photodiode inside a cryostat, you can convert an optical signal back into an RF signal, and you can use this to control a qubit. At the same time, to read out superconducting qubits optically, there's been many different approaches using quantum transducers, with mechanics, with direct electro-optic transduction, to really see that you can also, in principle, read out these systems with relatively high fidelity. And I'm going to dive a little bit deeper both into the readout and the control on the next few slides. So let's start with the control measurements that we've done in Delft. So essentially, let's start very simple. We need an RF signal, right? This is a collaboration between Rigetti, QBlocks, and QFOX. So we have an RF source from QBlocks that creates signals to read out the superconducting qubit. We then couple it to a Rigetti qubit with a readout resonator at 5.3 gigahertz. And this is then in turn coupled to a readout line where, maybe this is good without a pointer to quickly show. Here you have just the microwave readout line. So you can go into a HEMT and then can directly read out the state of the qubit through microwaves only. In addition, if you want to, you can also transduce then this microwave signal into an optical signal through an optomechanical transducer. You can upconvert it to hundreds of terahertz light, get it outside of the cryostat, and essentially do a heterodyne measurement. So really just a very sensitive phase measurement outside the cryo. Oh, that was too fast. The transducer itself, just to show you a little bit of the performance, it's a parametric process, so the more power we send in, the better the transduction efficiency. You see the peak is about at 4% here. We had a little bit of resonance from the readout resonator, but we get about a 3 dB hit. But nevertheless, it's relatively efficient. It's efficient enough to essentially demonstrate that you can read out this superconducting qubit optic. We're not doing the standard low power dispersive readout. We're actually working in the high power readout regime. So we first demonstrate that this actually works purely with microwaves. This is a technique that has been first demonstrated in Yale about 15 years ago. Essentially, when the readout resonator turns into the bare regime, gets into the bare regime, depends on the state of the qubit, if it's in the ground state or in the first excited state. The fidelities you can get here are up to almost 90%. This is pretty much at the theoretical limit of this high power readout regime. You can really nicely see we can distinguish between the ground and the first excited state in these measurements. Now we plugging in, instead of the pure microwave readout, we're plugging in our optomechanical transducer. You see here there's this little piezo block up here that essentially converts a microwave information into mechanical mode, and then we do an optomechanical transduction into the optical regime. And with this technique, we get a readout fidelity a little bit above 80%. So not quite as good as with the purely microwave approach, but still pretty decent, I would say. There's quite a bit of noise that we're adding, and this is really technical. We can hopefully get rid of this by, sorry, just give me a second. I'm talking too quickly, I think. Okay, so we can get rid of this through some technical improvements, I'll show on the next slide. What's important here is we can really read out the state of the qubit. We can do Rabi and Ramsey measurements of the qubit, all optical. So this is working pretty well with an 80% fidelity. One of the other really important things is that the T1 and the T2 stars of the qubit actually don't change when we do this optical readout. So that's something we were really happy to see, that if you put enough isolation essentially between the transducer and your qubit, you can really get rid of any reduction in T1 and T2 star of the qubit. Now, in terms of improvements that we can make is you can kind of filter the reflected light. There's some essentially spurious light coming back that's adding noise to a detection. You can also match the efficiency. You can make high efficiency. You can match the transducer and the readout resonator better. And very much like in the microwave domain, you can also include a tuba to just boost your signal essentially. So we think with this, we could get an improvement above 40 dB. So we should be able to do high fidelity, low power dispersive readout, single shot with this system. So this is promising. I think this is quite exciting. And I'll show you some numbers at the very end of how much this could actually improve the channel capacity for this typical superconducting qubit processors. Now, let me switch gears really quickly in my last 5 minutes or so and look at the photodiode approach that can allow you to get rid of some of this passive feed load now. So as you can see here, now I replaced essentially the input lines going in here, the coax lines here, with an optical fiber. An optical control system has a laser here, and then it's converted back into an RF signal here at the bottom. And again, the goal is to get rid of this passive feed load. So all these red bars on the bottom, we would ideally like to reduce so we can put more of these qubits into the cryostat. So passive feed load reduction, you can multiplex. Another nice thing is there's essentially no galvanic connection now from the outside into the fridge. It in principle is more compact. However, there's of course issues and people are really worried about shot noise from the laser, right? You have a very high power laser, produces a lot of shot noise. What is this going to do to the qubit, right? This is one of the main questions here. So we did some measurements on this. And essentially what we do is we read out the qubit with the microwave tone only. And we then send in the laser to the photodiode. We connect the photodiode through a circulator to the system. And right, you see then the qubit population as a function of the dissipated power in the photodiode. And you see, of course, if the photodiode is disconnected, in this case, these are the green dots here, there's essentially nothing happens. The qubit stays in the same state as it is if you don't have a photodiode in the system at all. Now, if the photodiode is at the mixing chamber and you directly connect the photodiode to the qubit, you will see a relatively strong heating of the qubit. You see an increase in the qubit population at relatively low optical power already. If you instead put the photodiode on the okay, great. If you put the photodiode at the still instead and put 40 dB attenuation between the photodiode and the qubit, you actually see that this, this effect of short noise is actually significantly reduced. However, of course, if you operate at the still, you also need a lot more power to drive the qubit. So what this means is, in order to really do kind of a pi rotation of your qubit, this is kind of the power you would need. So this is right in the regime where you actually start heating significantly. We start seeing the effects of short noise quite significantly. The same for if you put it at the still, there's already a little bit of increase in the qubit population, right? However, this is not as bad as it looks at first. So the important thing here is there is signs of short noise. However, you're really operating in a worst case scenario, right? You're continuously driving your photodiode, you're continuously driving your qubit. This is not really how you would ever control a qubit. You will always pulse your input light, you always pulse your input signals, and therefore you can actually reduce this significantly. And by how much I'm showing here. So this is too quick, sorry. Here, this is the same plot. So you see essentially now what I'm plotting on the x-axis here is now the pulse light. So it's on the very right is effectively CW, but if you reduce the time that you pulse, you see that you can actually get into a regime where you can really not see any effect of short noise. So this is kind of this green bar here. This is typically for pulse lengths of tens to hundreds of nanoseconds. You actually don't see much of an effect of the photon short noise on the qubit at all. So this is really promising to control the qubits. Even if there's short noise in general present in the system, you can have low enough powers to really do high fidelity kind of qubit rotations with these pulses. Just a few parameters on the qubit itself. This is the qubit that's been made in my group in Delft. And we then kind of look at what is the qubit doing when we drive it with optical control system. You see we can do really nice Rabi oscillations here on the bottom left. This is for 29 nanosecond pi pulses with a few hundred nanowatts of input power. And we look at how does the T1 of the qubit change when we send in optical power. There's a little bit of a challenge, I think, in general in our setup. I'm not sure where this is coming from, but our T1 is fluctuating quite a bit. And that's why we alternate between light on and light off measurements here, just to see if this fluctuation is coming from the light or not. And we clearly see this is very much correlated. So it's uncorrelated to the amount of power, but it's correlated with kind of the natural fluctuations that we see in the T1 of our system. The same is true for T2 stars. We could also measure that. Here's just a plot of the T2 star. We see actually that there's not really any effect of the light onto the qubit. So we really see this as a great approach to control the qubit. If you have your photodiode on the still and have enough attenuation in between, you can really nicely drive the qubit with this system. Now, this is one of my last slides. So it's really to wrap up. I'm set out to kind of get rid of some of this passive heat load, get rid of the heat load from the HEMT amplifiers. And there's essentially two paths to this. So one is, of course, replacing the HEMTs with transducers. We think you will need about, you can actually increase the number of readout lines by about a factor of 100 if you use transducers instead of the HEMTs. So I think this is quite promising. This could really get you into a regime where you can have a lot more qubits. Remember, not every qubit needs a readout line. You can actually have 5 or 10 qubits on a single readout line. So this could really be relatively big quantum processors already with this kind of approach. And then secondly, reducing the passive heat load through this photodiode approach. You can see if you don't have your light on all the time, but if you duty cycle it, if you send in pulses, you can also really reduce the heat load, and you can get into a regime. If you look here at about 1% duty cycle, you can increase the number of channels by a factor of 10 to 50 or so. So this is really promising in both directions for the passive heat load as well as for replacing HEMTs to increase the number of qubits inside the system. With this, I'm wrapping up. So this is the team at QPhox. This is really the people who have been building these systems. It's quite an exciting time. So the photodiode is kind of something that it's not just a research effort. This is not just data that we try to publish. This is really a product that we putting out now. So if you're interested in this, I have a slide with a little link at the very end. You can start talking to us. We're happy to give you a little bit more info, a little bit more technical details on this. This is my team in the university at TU Delft. There's quite a few people here from both the company and the team. The top one is the people from the group, and on the bottom is QFox. You also see we have a booth. So if you're interested, please come talking to us. Finally, this is what the system itself looks like. Scan the QR code if you're interested. Reach out. Be happy to start selling these as soon as you want them. Thanks.
Thanks a lot. Do we have questions?
Hi, can you hear me?
Yes.
Yes. So this is Thiago. Hi, Simon. Thanks for a
Thiago.
very nice talk.
Thank you.
I was just wondering, when you mentioned about the tupas and that you might need to have like amplifiers inside the diaphragm, how would that compare with the heat load that you were expecting, that you already have like for the RF amplifiers? Because you would have also to have like another or cables to drive your laser inside the fridge, or actually another laser? What is the strategy that you guys are thinking about it?
No, I think good question, right? For tupas, I think the tupas. So I'm not saying you will probably be able to replace all the coax lines. I think you will be able to replace a relatively big fraction of them. So you will not remove all of the passive heat load by any means. I think you could, in principle, remove all of this green bar here, the LNA load, right? So this is for the HEMTs. Of course, there's also some heating from the transducers. So this is, if you have the same number, you're going to have much less heating. You can increase it by 2 orders of magnitude, and you will have a similar heating there. For the tupas, you will probably need some additional lines going in there. So it's not like you will replace everything. But I think most importantly, the control lines is something you can get rid of. That makes sense. Yeah.
Shall we take one on this side? Is there a question? I have a non-physical question.
Sure, please.
So Creo is a collaboration with Rigetti, right? It's something that we've been seeing in the quantum technologies community, that startup companies are actually partnering up to solve problems. My question goes for how you do the IP for that.
Oh, you just make sure you don't work on the same thing. They work on the qubits, we work on the transducers. There's a very clear split in the middle. It's otherwise, this is true with any collaboration, right? You got to be really careful about IP, and you got to have good agreements beforehand. But ideally, you just don't want to work on the same thing together. I think that's really challenging. But happy to, if there's more question around this, happy to give some more tips on this. Okay, even though I'm not saying we're doing this perfectly by any means.
So a follow-up question on that. Dealing with export control.
Okay.
Because the companies are based in different countries, right?
Yes.
So IP, easy. What about export control?
That's definitely a challenging one. So in particular, right, so Rigetti, for example, send us their qubits. We have a QPU in Delft from them. They had to change the parameters of the standard system to send it to us, so it would not be subject to US export control. You can always get an exemption for export control. It's doable, but it's just a pain. And it was not needed to have this high performance systems for us to work with them. So, yeah.
One last question here on this side.
I love that this is now all the questions around that. Great. So please, Foko.
More technical question.
Please, yeah.
So you present here that the control lines that you need, right, for 144 qubits, 144 microwave, and 408 flux biasing. Can you shine a bit of light on how would you replace both with the optical control, or what are your thoughts?
So I think as a first step, we're looking into replacing the control lines. Again, you have short pulses. I think that's relatively straightforward. The flux biasing is something we're currently looking into. It's a little bit different beast, right? You're kind of applying a continuous current to your qubits. there it really depends. But this is something I think we still need to look a little bit better into. But I'm not saying this is not possible. I think this is just something you might need to optimize the system a little bit differently. So for the control, also for the control, there's many configurations, right? I'm telling you right now, we're working at the still, for example, is ideal, but it really depends on your qubits. It depends on your system. It might be better to work at the 4K plate. It might be better to work at the cold plate, for example. And the same is going to go for the flux biasing, I think.
With that, we can follow on. Thanks, Simon, again.
Sure, my pleasure. Thank you.
The next speaker is...
I didn't copy.
All right. Thank you.
Next speaker is Yiwen Chu from ETH Zurich.
All right. Yeah.
Oh no, it doesn't.
It's okay. I'll just stand here. Oh, whoa. Okay, wait. There. That's right. Is there a timer that actually didn't reset? But it's okay. I'll use my phone. It's okay. I got my phone here. That's fine. All right. Hello, everyone. I'm Yiwen Chu. I come from ETH Zurich, and thank you for inviting me to speak in this session. So I'll be telling you about some of our recent work on experimentally implementing a mechanical qubit in our group. So I'll start by first telling you what I mean by a mechanical qubit. So here is the quantum harmonic oscillator that we all know and love. It has these evenly spaced energy levels. Now, you can also have a quantum anharmonic oscillator. And what that means is just that your potential is no longer a nice parabolic potential. Instead, you have these energy levels that are no longer equally spaced. So for example, between the ground and first excited states, the transition energy is different from that from the first to the second excited state by, let's say, an amount alpha, right? And this is basically frequency difference that we call the anharmonicity. And now when we get to a regime where this alpha, right, is much larger than the dissipation rates in our system, then this is what we called the single excitation strong anharmonicity regime. Now, furthermore, if in between these two frequency scales, you can fit, let's say, some quantum operations, so let's say the speed of Rabi oscillations, then you get to a regime that we called the qubit regime. Okay, and this is, for example, the regime in which the famous transmon superconducting qubit operates. This qubit is basically just an anharmonic oscillator, where again, the anharmonicity is large enough compared to the dissipation that you can operate, you can do operations on this qubit. Now, what we set out to do was to see if we can create a similar beast using a mechanical system. And this is something that people have tried to do, right? So before we got into this business, for example, people in the group of Adrian Boxholz in IFO, have been and still are coupling, for example, carbon nanotubes to quantum dots. And they have been able to see sort of nonlinearities or anharmonicities arise when they get to a couple hundred phonons. But we're trying to really bring this to the single phonon regime. So the approach that we're going to take is somewhat similar to what Adrian is doing. We're going to take our mechanical oscillator and we're going to couple it to an already very anharmonic system. And in this case, it's our transmon superconducting qubit. All right, so the idea here basically is we take some mechanical resonator, we couple it to basically the electric field of this qubit by attaching a piezoelectric material to it, which will essentially then transduce the energy or the excitations between the electromagnetic and the mechanical domain. And that interaction is sort of given by this interaction Hamiltonian, which is just the overlap integral between the strain of the mechanical mode, the electric field of the qubit, and the piezoelectric tensor, which couples to. So you can write this in the quantum mechanics picture, right? Essentially what you end up with is a Jaynes-Cummings type of interaction between our qubit, which we're gonna just call a two-level system from now on, and our mechanical mode or our phonons, which to start with is just a harmonic oscillator, right? So you can write down the coupling strength of this system, which again just depends on this overlap integral and some physical parameters. Now, this Hamiltonian is, of course, completely analogous to cavity and circuit QED, of course. All right, so just to show you what our experimental system actually looks like. So here's a cartoon. What it consists of is basically two pieces of sapphire. And the top is our mechanical resonator. What we use are these so-called high overtone bulk acoustic wave resonators, which are basically sound waves that are trapped inside a crystal. Right? It's sort of bouncing back and forth between these two surfaces of a crystal. In our case, we also pattern actually a piezoelectric material, which is important for transducing the quantum information between the qubit and the acoustic modes. And in addition, we make it into this sort of curved surface. And again, here the analogy is just to an optical cavity. In order to have a stable Fabry-Perot cavity, right, you need at least one curved surface, and that's what we have here. All right. And then on our other chip, also made out of sapphire, we pattern our superconducting transmon qubit. Here's the X here representing the Josephson junction. You have your two capacitor heads, and this little antenna that sticks out of one of them, it's sort of indicated here by these purple arrows, is the electric field that once again allows for this piezoelectric transaction. All right, so this is what the device actually looks like in real life. Sapphire is transparent, so you can nicely see the qubit on this bottom larger chip here, and then you can sort of look, if you look carefully, there are these rings on top, which you can see a little bit better here. This is the curved surface of our acoustic resonator. This whole thing goes in a microwave cavity for readout of the superconducting qubit, and then that whole thing goes on the bottom of a Delft refrigerator. So again, all of our modes are at gigahertz frequencies, so if we cool it down, everything starts out in the quantum ground state. One other thing to note here is that actually our phonon modes, our mechanical modes, are quite long-lived, and they are actually quite a bit longer-lived than our qubits. Right? And that is a point that will become important in a little bit later in the talk. All right, so with this particular system, we have done quite a lot in our group in terms of quantum control of a mechanical mode, although so far, again, mostly we have been using it as a harmonic oscillator. Right? So we've been able to, for example, create different types of quantum states in our mechanical mode and sort of engineer, for example, interactions between multiple modes. But importantly for this talk, what I'm showing here is also our ability to basically control and read out the state of our mechanical modes, and in particular, perform full quantum tomography on our mode. So these are, for example, Wigner functions of our harmonic oscillator mode. And that is something that I won't go into detail here, but something that we will continue to use in our experiments. All right, so back to the mechanical qubit. So this is just to sort of show you the frequency landscape that we have in our system. We actually have a series of phonon modes that are spaced by about 12 megahertz. Again, this is because, right, we have a Fabry-Perot resonator, and that's just a free spectral range of this acoustic cavity. We place our qubit somewhere nearby. We usually work with one particular phonon mode, and it has this detuning delta. In addition, we have our readout cavity. That's this aluminum box that I showed you earlier. And close to that, we apply a microwave drive that performs the AC Stark shift on our superconducting qubit that allows us to essentially tune this detuning delta. Okay, so if we now look at the system consisting of the qubit and one of the mechanical modes, right? Basically what happens is that these two systems hybridize slightly in this so-called dispersive regime where the detuning is much larger than the coupling. And what you get are basically dressed states, right, of the mechanical and the qubit modes. And in particular, you can write it as the following. So in the dispersive regime, the Hamiltonian, this James-Cummings Hamiltonian set turns into this dispersive Hamiltonian. Here are two terms that are sort of relevant here. The first is the well-known dispersive interaction, which is actually what allows us to, for example, perform measurements of our phonon mode through the qubit. But the second term here that we're going to make use of is the fact that the phonon mode is going to inherit some nonlinearity, some anharmonicity from our qubit. And it is actually given exactly by this term here, right? This A dagger squared, A squared term is describing exactly, right, this anharmonicity. And if you diagonalize the Hamiltonian, you can actually find an analytical expression that tells you sort of the size of this anharmonicity. And it depends on, of course, our coupling strength and the detuning. And in particular, right, our coupling strength is sort of set by our device once we make it, but the detuning we can tune. And so what we can do is, for example, decrease the detuning successfully of our qubit to the mechanical mode and take a spectrum essentially of this mechanical mode. And what you see is here at large detuning is basically turquoise here, a nice sort of Lorentzian line shape that you would expect for a harmonic oscillator. As the detuning decreases, in blue here, you see that this line shape starts to become asymmetric. And this is a classic indication that you're entering this regime of so-called a Duffing oscillator. All right. And then as you keep going to even smaller detunings, what you see is that this line shape becomes even more asymmetric and becomes broadened. And this is an indication you're entering the qubit regime. And what you're seeing is actually some evidence of power broadening of the qubit. Okay, so this sort of qualitatively shows the evolution of the anharmonicity in our mechanical modes. We can be more quantitative about it and use basically a Ramsey sequence to measure the exact anharmonicity. Right? This is the usual thing where, if you want to measure a frequency, you do an interferometer experiment instead of just spectroscopy. And the way that it works here is actually we prepare, we start out with both systems in the ground state, right? We sort of swap half an excitation from our qubit into our phonon mode. And then we do another swap of another excitation from our qubit. Anyway, at the end of all this, but basically what you end up with is your qubit in the ground state and your phonon mode in a superposition of 0 and 2 phonons. Okay, now you put your qubit at the detuning at which you want to measure your anharmonicity, right? And after some interaction time t, actually what you get is a phase that is proportional to the anharmonicity and this interaction time. All right, and this is again in the rotating frame of the frequency between the ground and first excited state of your dressed phonon mode. And now basically to read this out, what you do is sort of reverse the whole sequence. And in the end, what you get is by just measuring the qubit state, excited state or ground state population, for example, you see basically these Ramsey oscillations that have a frequency that is, again, proportional to the anharmonicity alpha. Okay, so this allows us to very accurately measure the anharmonicity, and that's plotted in these blue points here as a function of detuning. So one thing to know here is the log scale, which is why all these anharmonicities are positive, but of course actually it switches sign with detuning. But you see here that it matches very well with our theoretical predictions. So the other important thing is we also actually measure the decoherence rates, the decay and decoherence rates of our mechanical oscillator. And you see that those actually also increase as you decrease the tuning. And this is what you expect because, again, the phonon mode is becoming hybridized with your qubit. And remember, our qubit is shorter lived than our phonon mode. And so it inherits not only the anharmonicity, but also some decoherence from the qubit. So you want to choose a point where your mechanical mode is still relatively long lived, but where your anharmonicity becomes much larger than the decoherence rate. And that is possible because the anharmonicity scales with detuning faster than the decoherence. Okay, and that's this point here where we get an anharmonicity of about 7.4 kilohertz, while our decoherence rate is about 2.5 kilohertz. So the other important thing is to choose a point at which you can still call this a mechanical mode or a mechanical qubit. And so by diagonalizing Hamiltonian, once again, we can see sort of what is the overlap of the stress state with the original purely mechanical state. And we find that at this point, it's still about 90%. So this mode is still mostly mechanical, right? And the fact that the anharmonicity is much larger than kappa potentially allows us to then make this a qubit. And to show that that is actually the case, what we can do is essentially, the usual thing you'd like to do with the qubit is to drive Rabi oscillations. So essentially what we see here is when we just directly drive this mechanical mode, instead of like a harmonic oscillator, right, you just sort of put more and more excitations in. Instead, what happens is, for example, you start out in the ground state, right? The population goes to the excited state, and then it oscillates back and forth. All right? And very little population ends up in the second excited state, as you would expect a qubit to do. All right? And the nice thing about our system is actually we can switch between it being a qubit and a harmonic oscillator, so we can do these Rabi oscillations after some time, stop, tune our qubit far away, and measure the Wigner function of our mechanical mode. And here, indeed, you see it goes from the ground state, to superposition to the first excited state is the Wigner function of a 1 Fock state, and it goes mostly back to the ground state. Okay, and so this was done sort of at an operating point where in here our Rabi frequency is about 10.6 kilohertz, and we're sort of parking that just in between our anharmonicity and our decoherence rates. And again, that's very important, right, to be able to do your operations faster than the time it takes to decohere, but slower than the anharmonicity such that you don't significantly affect the second excited state. Now, finally, to show fully that this is a qubit, the other thing you want to be able to do is prepare all cardinal points of the Bloch sphere of your qubit, and we show that indeed we can do that just by, for example, changing the phase of our drive. Okay. All right, so this was some work that was done by my PhD students, you and Igor, who are sitting in the back over there. Igor is actually giving another talk about this. If you want more details, you can look up his talk on Wednesday. And Yu is giving a poster at the poster session. All right, so just to finish up very quickly, what do we want to do with this, right? So of course, there are ideas of using mechanical modes to store and process quantum information, right? Now, this qubit is just another way, sort of another toolbox, right, that might allow us to perform more sort of operations on the single or multiple mode level. Another very important application of mechanical resonators is, of course, as detectors or sensors. So, with the famous example being LIGO. So we're actually looking into ways of using these H-bar resonators as sensors, and the fact that we can operate as a qubit now allows us to maybe use some of these sensing protocols that have been developed for qubit systems, like spins, for example, for magnetometry. Right now, we can apply those sequences perhaps to our mechanical mode directly. All right, so that's it from me, and this is a picture of our group, and again, the people who worked on this were Igor and you. So thank you very much. I'm happy to take questions.
Thank you very much. Perhaps we can start with the questions on this side. Do we? Well, perhaps I can ask a simple question. I'm not an experimentalist at all. So how do you think in the long run these mechanical qubits could compare with other technologies? Where do you think could have, let's say, a point against other technologies for making qubits?
Mm-hmm. Yeah, no, that's a very good question. I mean, as you see right now, right, our qubits, the pure properties of our qubit, right, for example, the Rabi rate or the the fidelity of our operations are not as high as state-of-the-art qubits. Again, we are just getting started. But some of the unique advantages here are sort of what I was talking about in the slide right here, where these mechanical modes really have these unique properties. One, the fact that they are mechanical, which means that you can use them to to talk to forces or have them interact with systems that you can't do with other types of qubits, right? So just to go into a bit more detail, what I'm showing here is, for example, there are proposals to use these mechanical modes to, say, detect gravitational waves, right? And that's, of course, a unique capability of a massive mechanical object, right? And this operation as a qubit is sort of just another tool that can help you do that, for example.
Okay, thanks. Gustavo, you can go on.
You have a question here? I have a quick one, Yiwen. So you operate in a regime where your qubit diabatically follows the mechanical system, right? So it's like a fourth or fifth lifetime-ish, right? So it's that from the numbers you had a table with, like, I think it was a fourth of the mechanical lifetime is the lifetime of the qubit.
Yes, right.
Right. So essentially your qubit instantaneously accommodates to the mechanical strain state where you're not quite here. So my question is, first, when you think about scaling, this the neat thing of your system is this very long lifetime, right?
Mhm.
And part of that arises from being really far away from the surfaces.
Mhm.
Right? You keep your modes sort of in the bulk
Yeah.
of your mechanical resonator. So
Right.
what changes would arise if you try to shrink things down and probably go into a regime where no longer your mechanical mode is live longer than the qubit, but you reverse
Yeah.
the hierarchy of the dissipation regime here.
Mhm. Yeah.
So what?
Right. Exactly. So I'm maybe I should emphasize this more, right? But being allowed to enter this mechanical qubit regime, this was really enabled by the fact that our mechanics, but also our qubit, are relatively long-lived. Of course, compared to our coupling strings, right? It's because of this exactly this, the fact that our mechanical mode, right, inherits decoherence from our qubit. So it's not just that our mechanical qubit needs to be long-lived enough. I mean, at this point, basically, you have some approximately equal contribution from the intrinsic decay of the coherence of the mechanical mode and the inherited decoherence from the qubit. So actually, both systems need to be quite coherent, right? So, but of course, both of those coherences are much, much larger than the time it takes to do your operations, then that's okay, right? But of course, you're right. If we started to change the geometry of our mechanical mode, that coherence can decrease. It could also affect the coherence of the qubits indirectly, right? In fact, our qubit coherences are in some sense limited by the fact that it's coupled to a mechanical system. So it's complicated trade-offs. Yeah.
Any further question? Can you come up, please, just so they can hear?
Okay, so we can switch.
We have one more here. And
We have more questions? Okay, go.
Yeah, thank you for the presentation, first of all. I wanted to follow up on the question asked before. Like if you consider it applying this technology for sensing applications, would you then also not expect that you probably, for making this system sensitive for the things you want to measure, that you're entering probably this regime? Like I can imagine now the frequencies to what you're sensitive are quite high, and maybe for the things that you can imagine sensing, you would like to have them lower. If you're talking about gravitational waves, for example.
I see. Yeah. Well, so actually, this this picture I'm showing here that I didn't explain at all is from a sort of proposal white paper about sensing gravitational waves at gigahertz frequencies, and that is the same thing that some people are interested in. Apparently, I'm no expert in this, but what you see there is that there are potential gravitational wave sources up to these very high frequency. But we are also actually working on decreasing the frequency of our resonators to again reach maybe more interesting regimes for these sensing applications. And it's not obvious that will necessarily let's say make them less coherent, right? In fact, some decoherent sources actually become less significant as you decrease frequency. So.
Then I think the vibrational environment of the cryostats, for example, might become more challenging.
At some point, yeah, exactly. There are many different loss mechanisms, noise sources, and they all scale differently with frequency. So we'll have to see what happens, basically. Yeah.
But is your ambition going to lower frequencies or not?
That is something we are thinking about doing. Yeah, we are starting to work on that. Yeah.
Okay, let's thank the speaker again. For keeping things on time. We're just a few minutes late, given that we started with a few minutes delayed. Excellent. Let me see if I recall the knob here.